So in this video, I'm going to show you guys how to make a slope field. And before I start showing you guys how to do that, just want to review uh, some stuff on slope, specifically how to graph slopes of lines with specific values. So slope is 0. When you draw the line, it will be horizontal, and if the slope increases, then the slope of the line should just get steeper. So this is a slope of 1, and a line with slope of 2 would be steeper than a line with a slope of 1. And similarly, a line with a slope of 3 will have a steepness that's greater than the previous one for 2. And if the slope is negative, then it will just be decreasing from left to right, but it will have the same steepness as the positive version. And then you might have slopes that are fractions, and so they lie between 0 and 1. And so if you start with slope of 0, the line will be horizontal. Slope of 1 will have this steepness, and any slope that are between 0 and 1, they will just be less steep than 1. So slope of 1/2, the line will be a little less steep than slope of 1, and a slope of 1/4 would be even less steep than a line with a slope of 1/2. So the reason why I'm going over the idea of slope and how to draw a line with these specific values is because when you're creating a slope field, we're basically just going to make a bunch of little lines that have specific slope. So just really quick, a slope field is a graphical representation of a differential equation. We'll talk more about differential equations, but as of right now, you can just think of it as an equation that gives us values of slopes at specific points, x and y. So for example 1, the differential equation we have here is dy dx equals y minus 1 over x squared. And we're going to use this differential equation to create the slope field that corresponds with this differential equation, which will give us a visual of what the solutions to this differential equation will look like. So to make it, we want to keep it organized because there are several points that we want to draw the slope at. And so below here, you have the space that you're going to make your slope field. And there's are 1, 2, 3, 4 x values and 1, 2 along the y-axis. And so there's a total of 12 points that we have to graph the slope through. So just to be organized, we're going to create our work in this table here. You guys can make it freehand. And I want to list all the x values that are on the x-axis along the left side of this table here, and then all the y values I'm going to list all across the top part. So it will look like this. So the smallest x value is -1. So I will put it here. And then the next one's 0, the next one's 1, and the next one's 2. So these are the x values going down that way. And then for the y values, I want to list them across the top from 0 to 2. So 0, 1, and 2. And then essentially what we're going to do is just plug these points carefully into the differential equation and just work out what the value is. And if you do each point one by one, you're going to be doing 12 separate calculations. So you can do that, but there is a more efficient way, slightly more efficient way of doing it. So if you do it one by one, I'll just do an example. So say I want to figure out the slope at when x equals -1 and y equals 0. So I'm going to plug into this equation. So it will be dy dx equals, my y is 0, -1 over x squared, which is -1. So I'm doing -1 squared. Then working that out, so it'll become -1 in the numerator and 1 in the denominator. Therefore, the slope is -1. So the differential equation equals negative 1 when x is negative 1 and y equals 0. And then you can do that again for negative 1, 1. So it will look like this. dy dx equals the y is 1 minus 1 over x squared. My x is negative 1 squared again. And so that works out to be 0 over 1, which is 0. So this value here is 0. So we can do that for the whole entire chart, and I'll just fill that in if you do that 12 times. This is what you'll get. So there's a faster way of creating the slope field for the same problem without having doing 12 separate substitution into the differential equation. So it comes with a little bit of analysis of the equation and thinking about what would happen for some specific x values and what would happen to the equation when you have specific y values plugged in. So one relationship that we can work off of is, here we have a fraction, and we know that if we are always dividing by, if the denominator is equal to 0, then the whole function will always be equal to undefined because you can't divide by 0. And so the denominator can only equal to 0 when x equals 0, because 0 squared will equal to 0. So we can use the fact that if the denominator is 0, when x equals to 0, that means we'll always get an answer of undefined when we plug it in. So we can write that in right away. Okay, similarly, we also have the case that if y is 1, then when we subtract 1 minus 1, the numerator will always be 0. So that always occurs when y equals to 1. And since the numerator is going to work out to 0, then the whole function would either equal to 0 or undefined depending on what is in the denominator. So for this y value of 1 here, 1 minus 1 is going to be 0. And then the denominator will work out to be negative 1 squared, which will be 0. So this will automatically be 0. Similarly, when y is 1 again and x is 1, the denominator will be 1 squared, so we have 0 over 1, which is 0. And then same thing, it doesn't matter if the x changes to 2. If the numerator is 1, then the whole differential equation will work out to be 0 again. So this is a quick way to create the values for those 6 points. And then if the denominator is equal to 1, we know that happens when the denominator equals to 1, that only happens when x is either negative 1 or 1. So if I do negative 1 squared here, then the denominators always go to 1, and the equation will just equal to whatever the y minus 1 is. So for this whole row, I don't need to plug in negative 1 for the denominator because I know it's going to equal to 1 no matter what. So it just depends on what the y value is. So 0 minus 1 gives you negative 1. 2 minus 1 is 1. And that goes the same way when x equals positive 1. When x is positive 1, the denominator works out to 1, positive 1, and what the equation equals just depends on what the numerator is. So again, when y is 0, 0 minus 1 is negative 1. And then when y is 2, you get 2 minus 1, which is 1. So you just create those 2 more points. And then for these, there's no really good shortcut. You can just plug them in and then figure out what they equal to. So I'll just do that on the side. So dy dx equals, so I'm going to plug in 0, 4 to fill in this value. I'm going to plug in 0, 4, y. So it's 0 minus 1 over, and it's x squared. My x here is 2, so it's 2 squared, and that works out to be negative 1/4. Okay, and then similarly for the point 2, to fill in this value, that's when x is 2 and y is 2. So there'll be dy dx equals, my y is 2, 2 minus 1 over my x squared, which is 2, so it's 2 squared, which equals 1 over 4. So now we have the whole chart filled in for a set of x value and y value. And then what you do from there is you're going to plot each point. Go to each point and graph the corresponding slope. So all these are all the slope values. Okay, so now we're going to transfer the information we have in the table onto the slope field setup. And I'm just going to go one by one. It's easiest to start with the slopes that are 0 because those are quicker to draw in. So I have a slope of 0 at the point negative 1, comma 1. So negative 1, comma 1, a slope of 0. So we draw a line that's horizontal through that point. And then there's another slope of 0 at 1, comma 1. So 1, comma 1, slope of 0. And then another point that where the slope is 0 is 2, comma 1. So 2, comma 1. So those values all have slope of 0. And then we can do the same thing with all the other points. So I'm going to do the next one is going to be the positive ones. So there's a positive 1 slope at negative 1, 2. Negative 1, 2, positive 1. And then there's another one at 1, comma 2. So we're trying to make them similar. And then we can do the negative ones, which will be opposite direction of the previous one that we made. So that's at negative, this one here is for negative 1, comma 0. So that's opposite. And at 1, comma 0. Too steep. And then that's it for negative 1. And then the last like numerical value we have here are negative 1/4 and 1/4. So 2, comma 0, that's right here. And the slope is negative, so I have to go in this direction, and it's negative 1/4, so it's going to be less steep than the slope for 1. So just try my best to draw it so it's less steep. And then at 2, comma 2, it's a slope of positive 1/4, so I'll draw it similar to the steepness of this one, but in the positive direction. And then for the undefined ones, these 3 here, you don't need to graph those, okay? So for when the value, the slope value is undefined, you can just leave it blank at those points. So that's 0, 0. Here you can leave blank at 0, 1 and 0, 2. So the product we have here is called the slope field. So we're going to do a second example. So here's a differential equation, dy dx equals negative xy squared over 2. And I'm going to set up my table with the x and y values. I draw these bold lines in just to make them clear. And then my x's are going to go down that way. I'm going to list my y's the other way. So my x values are from negative 1, 0, 1, 2, same ones as before. So negative 1, 0, 1, 2. And my y values are from 0 to 2. So 0, 1, 2. Okay, so again, you can do the slower way, but you'll still get the task accomplished is by plugging each of these points one by one into the equation. So let's just do one as an example. So say I want to find the value of the differential equation when x is negative 1 and y is 0. So where I see x, I'm going to plug in negative 1, and where I see y, I'm going to plug in 0 to fill in this value. So it will be dy dx equals negative, my x is negative 1, times my y squared, so that's 0 squared over 2. And that works out to be 0 over 2, which is 0. So this value here is going to be 0. I'll do one more. And so say I want to find the slope of the line at the point negative 1, 1. So we'll have dy dx equals, my x is negative 1 and my y is going to be 1. So it'll be negative times negative 1, 1 squared over 2. That's going to give me, this is 1 times 1, so it's going to give you 1/2. So this value here will be 1/2. And you can do the same thing for the rest of them. So that's the kind of slow way of doing it, where you're plugging each pair of x and y into the differential equation and just working out what it equals to. Try to do example 2, trying to figure out some useful relationships that will help me fill in the table a little quicker. So I'm looking at this equation here, and again, we're running into a fraction. So, but this time the denominator is 2. So I won't have to worry about getting undefined or anything because the denominator is always going to be 2. But I do want to pay attention in the numerator. I can see that I have, if the numerator is 0, then whatever x and y makes the numerator 0 divided by 2 will equal to 0. So that will happen either when x is 0, the numerator will work out to be 0, or when y is 0, the numerator will also work out to 0. So where I see x is 0, I can automatically draw in 0. And then similarly for when the y is 0, the whole numerator will be 0, so I can put a 0 here, 0 here, and 0 here. So basically, just by thinking about the equation a little bit, I can fill in 6 of the spots quickly. And then now I can think about, I see a square here, so the job of a square will change it equal to 1, and no matter if the y is a positive 1 or a negative 1. So in this case, I only have positive 1 to worry about. So when y is 1 squared, that will always just be 1. So I just need to care about what the value of the equation will be. I can just pay attention to just basically this part, because when y is 1 here, when it's 1, then that always just equals to 1. So I can just pay attention to this. I can ignore the y. So when x is negative 1, then negative 1 times this negative will give me a 1 in the numerator divided by 2, so that'll be 1/2. And similarly, when x is 1 here, negative 1 over 2, they'll give me negative 1/2. And then when x is 2 here, negative times 2 divided by 2 is going to give me negative 1. So now I get to look at when the y is 2 and Same thing, it's gonna work. This is always gonna be a 4. I think I'm gonna have to work these three a little carefully just because um, I can't ignore part of the equation. So I'm gonna take everything one by one. Um, so I'm gonna do that. So dy dx, to fill in this point, the x is -1 and the y is 2. So it's gonna be negative times -1 for the x, 2 for the y squared over the 2. That's going to give me 4. 4 divided by 2 is 2. And times this positive 1 will give me um, positive 2. So this will be a positive 2. And then I'm going to fill in this spot here. So it's going to be dy dx equals, and it'll be negative times -1. My x is going to be 1, and my y is 2, so it's 2 squared again, all over 2. So this is 4 times -1, so that's going to give me -4. -4 divided by 2 is going to give me -2. And then to fill in this spot, we'll have dy dx equals negative times 2 times 2 squared divided by 2, and that's going to work out to be, that's -2 times 4, which is -8. -8 divided by 2 is going to give me -4. So for those last three, I just had to kind of plug and chug and just carefully work it out to make sure the signs are correct. So this will be the complete table that contains all the slopes that I need that I'm going to transfer over to the final step is to transfer the information from the slope field over to this. So I'm going to take the steps here. So I'm just going to use red. So I'm going to graph the zeros first. So that's going to be at -1, 0. And then, so basically where the x is 0, so that's the whole entire x-axis. And then also that was when the y's were 0. So I can put horizontal lines through those points. So I'll do those really quickly, and then I'm going to take care of the other ones. So here we have a slope of -1 at 2, 1. So 2, 1, slope of 1. Oh, there's a -1, so I'm going to go in the other direction. And then, so this is done, then I can take care of the other one. So I'll do the 2's and the -2's first. So there's a slope of 2 at -1, 2. So I'll make it kind of steep. And then at 1, 2, it's -2. So 1, 2, it's the opposite direction. So I'll make it similar steepnesses to that one. And then I'll take care of the -4, which is at 2, 2, 2, 2, and that one's positive, negative, so I'm going to make it steeper than this one, which is -2. And then the halves. So at -1, 1 is +1/2, so I'll make it less steep than the 0, more steeper than the 0, but less steep than everything else. So it looks like that. And then at 1, 1, it's a -1/2, so it's going to be equal to this steepness, but in the other direction. So that's the complete slope field for this differential equation. So a word about, in terms of the amount of work, you need to make sure you can use your relationships and then show a little bit of work in terms of the, the harder ones, maybe you want to plug them in, but I do want you guys to think about the relationships that you can use to make the fill in the table quicker. But one way or the other. If you do it faster or slow, it's a matter of um, time that you have. So it's more advantageous for you to look for relationships if you have not a lot of time. But if you have all the, you know, plenty of time, then you could do each of the 12 calculations. But I would think most of you guys would want to use relationships because, when we figured out that if y or x is 0, we were able to just fill in these points and it made it go faster than having to plug it in. Um, so that's the expectation, is to show as much work as you need to complete the table and try to use relationships, and then carefully transfer them over here and make sure you guys do it in an organized fashion. So I did it with the zeros first, then I'll do the ones that are positive or negative each other for next, and then just carefully making them um, accurate. So that's how you guys make a slope field for a differential equation.